Your brain doesn't rejuvenate through sleep by simply resting. Instead, it undergoes active waste clearance. Contrary to the belief that sleep merely rests the body, neurons shrink by 60% during slow-wave sleep. This opens space for cerebrospinal fluid to clear toxic proteins like beta-amyloid. Studies from the University of Rochester in 2013 showed this glymphatic system is 10 times more active during sleep. As you miss sleep, these toxins accumulate, potentially contributing to memory impairment. Every hour of missed sleep disrupts this cleansing, laying groundwork for neurodegenerative diseases. Glymphatic flow is crucial, but misunderstood. Feeling tired isn't just from lost hours. Adenosine buildup in your brain elevates fatigue. This neurotransmitter accumulates every waking minute. When you sleep, your brain clears adenosine, resetting your alertness. A 2017 study from Stanford University revealed that just one night of restricted sleep can increase adenosine levels by 30%, making you feel sluggish. People often mistake this chemical fatigue for a lack of motivation. The real issue lies in cellular energy not being reset due to inadequate sleep. Your neurons need this downtime for optimal function. Many believe energy dips are about willpower, but cortisol plays a pivotal role. This hormone follows a circadian rhythm, peaking in the morning to wake you up. Chronic sleep loss skews this cycle, leading to higher evening cortisol levels. This disrupts your energy regulation, making you feel wired but tired. A 2021 meta-analysis in Sleep Medicine Reviews highlighted that cortisol levels can remain elevated for 24 hours after sleep deprivation. This hormonal imbalance is misunderstood as just being stressed, but it's a physiological response to poor sleep. REM sleep isn't just vivid dreams, it's a critical phase for emotional regulation. During this stage, your brain processes and integrates emotional experiences. Skipping REM can heighten emotional reactivity. Research in 2019 from Harvard showed that reducing REM sleep by 25% increased emotional volatility by 60%. It's not your mood, it's your brain missing essential processing time. By underestimating REM's role, we misunderstand our emotional balance. Each night of disrupted sleep means losing this crucial processing period. 1 week of poor sleep affects more than tired eyes. It alters genetic expression. A 2013 study from the University of Surrey found that over 700 genes change behavior after just 1 week of sleep deprivation. Genes linked to inflammation, immunity, and stress responses are upregulated. Misunderstanding sleep as just static rest ignores how deeply it interacts with DNA. Your body isn't simply tired, it's genetically altered by sleep loss. This molecular shift provides a stark contrast to the idea of sleep as merely downtime. Inside your brain, adenosine receptors regulate fatigue. As adenosine binds to these receptors, it inhibits wake-promoting neurons. Caffeine, a common countermeasure, blocks these receptors, masking tiredness but not clearing adenosine. The blockade lasts mere hours, but the adenosine remains, building pressure for sleep. When you finally rest, the brain clears adenosine via glial cells in a process modulated by the basal forebrain. This molecular dance illustrates why caffeine doesn't replace sleep. Prolonged receptor engagement without clearance intensifies sleep pressure, explaining post-caffeine crashes. During sleep, your brain's glymphatic system clears metabolic waste via aquaporin 4 channels. These channels, embedded in astrocyte and feet, facilitate fluid exchange, crucial for neurotoxin clearance. A 2020 study from the University of Copenhagen highlighted that aquaporin 4 activity peaks during non-REM sleep stages. This efficient waste removal reduces risks of neurodegenerative diseases. Disrupting this process, even for a week, can impair cognitive function. The glymphatic system's efficiency is a testament to evolutionary adaptations ensuring brain maintenance during sleep. Circadian oscillator genes orchestrate cellular rhythms, synchronizing sleep-wake cycles. Clock and BMAL1 proteins form a complex regulating transcription of period and cryptochrome genes. This molecular feedback loop influences melatonin synthesis in the pineal gland. Jet lag or shift work disrupts these genes, leading to circadian misalignment. A 2019 study in Nature Communications showed significant changes in 5% of the transcriptome after sleep deprivation. These oscillators don't just dictate sleep, they govern metabolic and hormonal cycles, illustrating the depth of circadian regulation. The cortisol awakening response peaks within 30 minutes of waking, driven by hypothalamic pituitary adrenal axis activation. It's a surge preparing your body for stress. Sleep loss blunts this response, impairing stress resilience. Research from the University of Westminster in 2015 noted a 50% reduction in cortisol peak following sleep restriction. This not only affects alertness, but also immune function. Cortisol's precise morning spike underscores its role in daily preparedness, disrupted by inadequate sleep. Understanding this reveals how sleep intertwines with endocrine health. REM stage sleep is pivotal for memory consolidation. During this phase, hippocampal neurons fire in patterns replicating daytime activity. This process, termed replay, strengthens synaptic connections. A 2018 study published in Science demonstrated enhanced learning when REM sleep followed training. Deprivation affects synaptic plasticity, reducing retention of new information. The brain's ability to replay experiences relies on uninterrupted REM cycles, crucial for long-term memory. This intricate neural rehearsal showcases the active nature of sleep beyond mere rest. Chronic sleep debt accumulates differently than acute deprivation. Acute loss involves immediate cognitive deficits, like impaired reaction times. Chronic debt, however, involves gradual metabolic changes. A 2021 study from the University of Colorado found that after 1 week of restricted sleep, insulin sensitivity dropped by 30%. This creates a prediabetic state, independent of diet. While acute deprivation is felt immediately, chronic debt subtly alters glucose metabolism over weeks. Understanding these distinct pathways reveals how persistent sleep loss undermines metabolic health differently. Sleep tracking apps often miss nuanced physiological changes. Polysomnography, the gold standard for sleep study, measures brain waves, oxygen levels, and heart rate. It identifies sleep stages with precision. In contrast, consumer apps infer sleep from movement and heart rate, often misclassifying sleep stages. A 2022 review in Journal of Clinical Sleep Medicine showed discrepancies of up to 30% between apps and polysomnography. Apps provide a broad overview, but they lack the depth to detect subtle sleep architecture disruptions. This highlights the gap between consumer technology and clinical accuracy. The wellness industry often promotes sleep aids, yet peer-reviewed literature emphasizes natural regulation. Melatonin supplements, while popular, don't address underlying issues. A 2023 meta-analysis in Sleep Health found limited efficacy for chronic insomnia. Instead, melatonin resets circadian phase, effective primarily for jet lag. Long-term reliance can desensitize receptors, reducing natural melatonin production. This contradicts the narrative of quick fixes, revealing a deeper need for lifestyle alignment with natural rhythms. True solutions lie within behavioral adjustments, rather than external supplements. Long-term sleep deprivation alters brain structure. MRI studies from the University of Oxford in 2020 demonstrated reduced gray matter volume in the prefrontal cortex after 6 months of poor sleep. This area governs decision-making and impulse control. Such structural changes correlate with observed cognitive and emotional dysregulation. These findings challenge the assumption that sleep loss merely causes temporary fatigue. Instead, sustained deprivation engenders tangible anatomical changes. This raises questions about sleep's role in maintaining neural integrity over time. One illuminating study from 2019 in Science Advances showed that sleep-deprived individuals aged their DNA by up to 2 years within a matter of weeks. This was assessed using epigenetic clocks, which measure biological age. The study highlighted that recovery sleep failed to fully reverse these age markers. Such findings redefine sleep debt as more than just a temporary state. It underscores a profound alteration at the genetic level. Understanding this biological impact reframes how we view nightly rest, revealing its deeper implications on aging.